First, thanks for kind introduction. My name is Veljko Stefan from the Faculty of Technology and Knowledge, University of Belgrade, the Department of Metallurgical Engineering. My task today is to present some of the results of the continuous drive friction welding of aluminum and copper, as well as aluminum copper alloys. And I hope that most of you could find some of the information interesting because of we have a lot of metallurgical aspects in this. Okay. In this paper. Okay. First of all, why welding of aluminum and copper, as well as aluminum and copper-based alloys? The thermoenergetic plants, as well as their transmission systems, ask for a lot of connections for current transmission, and nowadays the price of aluminum is a lot lower than the price of the pure copper, electrolytic copper. So there is a tendency to change at least some parts of the copper systems with aluminum parts. In that manner, we have decided to investigate the effect of continuous drive friction welding on the strength of the welded joint, as well as the conductivity and the resistivity of the welded joint. Well, during the investigation, we faced a lot of problems. First of all, the chemical and the physical properties of aluminum and copper are very distinct. Chemical affinity between those two elements is very high. In that manner, there is a tendency to that aluminum and copper form a lot of different intermetallic compounds. We used this designation AlxCuy, and you will see the reason for that kind of designation. So it was critical to use an appropriate welding method in order to create good aluminum copper joint. And there we are coming to the reason to choose the I don't know what's going on, but continuous drive friction welding. In all of the commercial fusion welding technologies, there is a high heat input into the welding joint. In that manner, we provide all the necessary propositions to form the whole variety of intermetallic compounds between aluminum and copper. And if we know that those compounds are brittle, they have a poor effect on the conductivity of the welding joint. In that manner, we have to choose some kind of some of the technologies with the minimum heating. That way, we have decided to investigate the friction welding with the less or the least heating. And what are the influential parameters? The friction pressure, friction time, forging pressure, forging time, and rotation speed as well. So again, we have problem with PowerPoint presentation formats. So we have some marks here, but there should be presented some of the equations which we used in design of the technology. Yeah, probably. So I have decided to present the very simple machine we used in our experiment. Actually, one of the Serbian companies helped us with design of the machine, and we have produced a lot of different samples of welded joints between pure aluminum and pure copper on that machine, and we made amazing results. here are the represented the welded samples, and as you can see, the welded joint between aluminum and copper is characterized by what we called mushroom. Yeah, this is the extent of the aluminum which yielded out of the welded joint, and before each application, you have to machine all these parts to get the pure layer. So, as I said, there is a whole variety of intermetallic compounds. For example, IL2Cu, IL4Cu9, and ILCu. And what's the importance of the mentioning the variety of the intermetallic compounds? The strength of the interlayers, because between each compound is wholly different. So before our investigation, we knew that strength of the intermetallic layers is weaker than the strength between intermetallic layers and the pure aluminum or pure copper. But during these investigations, we have found out that effects of AlxCuy intermetallic compound might be crucial in terms of improving its strength during exploitation. So, as I said, our aim was to investigate first of all the formation of those intermetallic compounds during dynamic and static conditions. In terms of dynamic conditions, we mean welding, and static, the heat treatment. Okay, so we used to vary the parameters during the welding in order to obtain the different heat inputs in the welding joints, so to produce a whole different types of the intermetallic layers. Two sets of the welded joints were made. The first one for, let's say, the dynamic testing, and we varied the friction time. The friction pressure, forging time, forging pressure, and rotation speed were the same. So the second set was the heat-treated samples. They were made by with the similar parameters to those of the welded sample joints. Here we wanted to provide the as thick intermetallic layer as we could. So we made it at the end. But what's the importance? The first sample was without heat treatment at all. The second one was heat treated at 325 degrees for 1 hour, and then air cooled. And the third sample was heat treated at 325 degrees for 12 hours. So when we finished all the production procedures, we prepared some of the metallographic samples, and that's the look. Yeah, as you can see, this is the mushroom I spoke about. This is the excess of the aluminum, which yielded outside of the welded joint. And what's the importance? When we are talking about the welded joints made by continuous drive friction welding, we have whole different regions through the cross section, the central region and the peripheral region. So we will discuss about the influence of parameters on the production. So during the production, we used to follow whole process by thermography. In that manner, we can see that. I'll just go back. As I said, we have 3 different samples, and the only parameter we varied was friction time. So with the increase of friction time, as we expected, we obtained the higher temperatures in the welded joint. And what's the importance of the measuring those temperatures? It's to try to combine those informations and to explain the kinetics of formation of intermetallic compounds. So in that manner, we have the higher temperatures for the third sample, and as you can see, all these changes which we followed were divided into two regions. First one was let's say friction dominated region, and the second one is followed by forging. So at the beginning, there is a friction which generates the important heat, and then when the samples were heated enough, then the pressure becomes to dominate and allows us to form solid joints. So during the metallographic analysis of the welded joints, we could distinguish that, for example, for the shortest friction time, we have obtained AlxCuy intermetallic compound on the interlayer between aluminum and copper. So what's the importance of this? Maybe it's hard to see from these pictures, but the intermetallic layer is not continuous. It has variations of thickness and also discontinuities. So with increase of friction time, we obtained continuous AlxCuy intermetallic layer, but Al4Cu9 intermetallic layer starts to form, and Al4Cu9 layer is now discontinuous. All those discontinuities in the intermetallic layer weakens the welded joint. Finally, for the longest times, we obtain continuous Al4Cu9 and Al2Cu intermetallic layer, but also there is formation of AlxCuy layer, which we'll present a little bit later. And when we are talking about the samples which were heat treated, all the samples show the continuous intermetallic layers all over the surface. So what's the difference? The first one contains only Al2Cu intermetallic layer. Then the second one contains also Al4Cu9, and the last one, as you can see, contains AlxCuy intermetallic layers, which is formed between those two intermetallic layers. And as I said, they improve a lot mechanical properties of the joint. So as I said, during the simulation, during the heat treatment and the welding, we obtained similar intermetallic composition in welded and heat treated samples, but there are some differences in central region and peripheral region. So the thickness of the intermetallic layer in the peripheral region was higher than in the central region. Mechanical properties showed slightly different results than we expected. In that manner, we can see that even, let me show you, even for thicker intermetallic layers, we obtained higher strengths. That was probably the highest breakthrough of this paper. So if you thought that thicker layers provide poor mechanical properties, this is something wholly different, and provides us a lot of space to investigate the strength of the intermetallic layers and the strength of the sub layers, especially. So what's the I think obvious from this presentation is that the main difference between samples which we made during the continuous dry friction welding and heat treated samples was the homogeneity of intermetallic layers. During heat treatment, we obtained more homogeneous in terms of composition and in terms of thickness intermetallic layers. So joints heat treated at 325 degrees Celsius for 1 hour contain an intermetallic layer with continuous IL2Cu and IL4 Cu9 sublayers with a total thickness of approximately 1 micrometer. Those joints exhibited higher strength and ductility compared to joints produced with a friction time of 2 seconds. So intermetallic layers consist with continuous IL2Cu sublayer and discontinuous IL4 Cu9 sublayer with a total thickness of 0.8 micrometer shows a different mechanical properties. Joint made by heat treatment at 325 degrees for 12 hours, they showed intermetallic layers 7.3 micrometers thickness and composed of those 3 sublayers and demonstrated higher strength and comparable ductility to those of the made by friction time of 4 seconds. So the intermetallic layer was 1.6 micrometer thickness thick and consists of IL2 sublayer and this continuous IL2 sublayer and discontinuous IL4 Cu9 sublayer. So overall, heat-treated aluminum copper joints exhibited high tensile strength, and those strengths were higher than those formed by varying the friction times, despite more substantial intermetallic compounds. Interlayer developed in terms of thickness and phase composition. This outcome does not align well with the current understanding of CDFW joining of aluminum copper alloys. And in that manner, we will proceed with our investigations and try to explain what are the relations between those layers and the pure methods. So thank you for your attention.